Like a carousel, and you want it to move continuously all the time, right? But then if people jump on and off, it kind of reacts on that. So it kind of stops and it doesn't really work. You don't get the nice flow you want. So, but then if you add like then a big rotating mass in there, or a synchronous condenser, then you continue to have this smooth turning all the time.
The response is based on physics. If there is a frequency change, the response will be based on this change in physics, change on the rotation of the machine. The inertia will be provided. No control functionality, purely physics.
Now, this data center example, it's almost like an extreme case study in how fast and violently load can shift. And I think it raises a question that I imagine many listeners are already asking themselves, which is what you've mentioned a few times already, Christian, which is, could a software-based solution like a grid-forming battery or a StatCom respond quickly enough to handle this? When we talk about the energy transition, we often talk about what it is that we're adding, whether it be solar panels, wind turbines, battery storage, or transmission lines. We talk about costs, we talk about capacity, but what we talk about less is what we are quietly losing when retiring fossil fuel plants. And the backbone of the power grid isn't simply coal and gas plants that are generating electricity. It's also the physical properties of those machines. Fuel aside, these machines at their core are enormous spinning rotors. They're synchronized to the grid, and this intrinsic property of inertia in the rotor acts as a kind of mechanical immune system for the grid. It absorbs shocks, it steadies frequencies, and most importantly, it buys grid operators the seconds that they need to respond when something goes wrong. And all of this happens automatically, instantaneously, and without any kind of sophisticated software code. But as these plants retire, that immune system retires with them. And at the same moment, a new and extreme stress test is coming onto the grid in the form of AI data centers. Loads that are so volatile that they can swing from drawing 500 megawatts to pushing 50 megawatts back onto the grid in a tenth of a second. And of course, the grid was not designed for this. So the question is, what fills that physical gap? Whether it can be filled by software, by batteries, or whether it requires something else that actually spins, is one of the most consequential and underappreciated subjects in the energy transition. And so today we're getting into all of it, and I'm joined by Kristina Carlquist, General Manager of Synchronous Condensers at ABB, and Christian Pyrl, Sales Manager of Synchronous Condensers at ABB. Welcome to the both of you.
Thank you very much, Bridget.
So I touched on it briefly in the introduction, but of course we want to hear a more detailed explanation from both of you experts. As coal and gas plants retire, what is it that the grid is actually losing beyond generation capacity?
If I start from the technical point of view, you can say this is system strength. Now, when we speak about system strength, it sounds very simple, but it's a combination of things. It's something we call inertia, which you mentioned before, which is helping keeping the frequency stable. It's system strength also is fault currents, and that means how voltage are impacted in a network, and also reactive power, which is needed to regulate the voltage. All that can be delivered by some units which provide system strength. And then we are coming to synchronous condensers, which is a natural way of doing that without any fancy electronics.
So you mentioned inertia. This is what stabilizes the frequency and gives the operators time to act. This reactive power and voltage control, though, can you explain that a bit more?
Yeah. When you have a system and you run your operation of your system, different type of generators are normally participating in regulating the voltage. And depending on which voltage levels are you're operating, if it's transmission network or if it's in the distribution level, there is a different amount of reactive power will have a different impact. Where in transmission network, 50 MVRs may only impact the voltage very little. Where in the distribution network, this has a major impact in the voltage of your network. So it depends very much how reactive power can act. In the transmission network, reactive power is much influenced by the reactances, while in a distribution network it's impacted also by resistance, that means by the loads itself, so that you can get a voltage dip caused by a big load. This maybe not happen in a transmission network such easily, because there you have more strength, it's more based on reactances, so there the requirements of reactive power are important, but not as much important.
So just to clarify about this reactive power, this would be almost a kind of stabilizer to changing conditions, especially for renewable conditions that might be attached or connected to the grid.
Reactive power means in reality voltage regulation. Voltage stability is not only voltage regulation. Voltage stability means also to withstand a failure in a network or a big change in a network. And that's something different, which is not easily always handled only by reactive power. It's also by something which we call fault current contribution. And that's the reason where synchronous condensers an important role to play, because they act like a generator or rotating machine by providing that.
Okay, so we've got inertia, this short circuit current or fault circuit current, and then reactive power as well as the three services that these fossil fuel generators on the grid are helping with. Now, I guess my question would be, what happens then when you have an inverter-based resource that comes in and replaces them, like a solar PV system or a wind turbine or battery or a fuel cell? What happens when you get a lot of those on the grid?
One thing what is happening is that of course, when you have inverter-based power generation, this type of generation is not participating with fault current contribution. That this means that it's not pushing up the fault current level in a network. You are generating your active power, you are participating in reactive power by helping regulating the voltage, but it's not giving system strength itself, which normally rotating machines do and did. So we are losing that. And that's the reason why these rotating machines with synchronous condensers provide this additional service.
And I think we see now with all this renewable, which is fantastic that we get to the grid. And at the same time, we're removing some of this, like you call it, system strength facilities or whatever we call it. But and so it really, we need to add something more to it to keep it in the same stability of the grid as we have had before. New challenges.
What do those frequency impacts actually look like from grid studies that you've done or technical work that you've been involved in? What does it look like?
You know, if you look over a season, let's say a year, then you can see that in times when you have very high loads, that means during winter time in Scandinavia when you need a lot of heating, there will be a lot of generation connected to that. Automatically with that, because there is a lot of generation, not only renewables, but also thermal power plants are connected, maybe nuclear power plants are connected during that time. And those units are providing enormous amount of inertia. So that means that during high load seasons, the inertia values are normally very high. But when it comes to times where you have low load consumption, or where you have enormous big amount of wind and solar participating during summertime, then automatically the inertia is coming down. And this means those impacts which you may get by a frequency variation, if then a big thermal power plants drop off, or if a big load is connected, then this is impacting the frequency much, much more during those low power seasons. And this type of change could be, as I described before, seasonal during a season, but this can also happen during a day, during nighttime. For example, we have low inertia levels, low fault current levels. And then, of course, those consequences of a failure in a network or impact on a network can be a disaster, as we saw also in Spain.
Right. Okay. So this low levels of inertia, this means that in a low inertia period that grid operators are really losing the physical buffer that buys them the time that they need to respond in order to avoid a blackout. Is that right?
Yeah, you can say so. And also, I would say in general, based on the way how the market is acting, that transmission system operators are not anymore in control, because the market is defining if we want to buy wind power or solar power because it's less expensive, or if we buy nuclear power. It's not anymore the TSO's decision which way to go. It's the market's decision. So they have to react on these changed variations and still create a power system which is stable enough for a new society, or for our society which we have now, where we are relying on reliable power.
So then what is it that these utilities and TSOs are expressing to you directly about this? Are they alarmed? Are they still catching up? Are they coming to you for help? We need those synchronous condensers?
I would say in general, it's a mixture. Some transmission system operators, they're coming to us and say, what would be a big data center? What is the implication? What should we think about? Is there something which you can help us with in recommendations? Is there something we need to develop on the grid code? And some utilities are very good in knowing that by themselves, because they are acting, they have experience on that already. Maybe they have even had bad experience. And of course, based on that, they are more aware of what to do and what not to do.
And I would also say it looks a little bit different in different countries, which kind of philosophy the country have, what kind of policies they put in place to make sure to have the system strength. So, for example, in Spain, more or less, if you want to connect with renewables, you also need to make sure that you can contribute with ancillary services. And the same if you go, not exactly, but a little bit the same in Australia. They have the renewable zones where they also need to keep a certain stability within the zones. And they have a different way of making sure they have the services in UK, for example. So it looks different in different countries. And Ireland is another example where they have kind of looked at a broader view, how to find the market, how they can contribute with the ancillary services.
I would like to come back to these differences in geographies and ancillary services, but I want to talk about synchronous condensers now, as I'm sure you're both dying to. But basically, we've got these coal and these gas plants that were providing all of these benefits of inertia, voltage regulation, essentially for free, just as a byproduct of having a spinning machine on the grid. And synchronous condensers are a way to that now decouple those services from generation entirely. So I want to talk about what actually is a synchronous condenser, because it sounds very fancy. But I think the physics here can be kind of counterintuitive. Now, I've seen a synchronous condenser described as a shock absorber for the grid, or like a spinning flywheel that just wants to keep spinning. Do either of those land for you, or is there a better way to maybe put it or phrase it?
Kristina, you had a nice example, which you mentioned for me once.
The carousel.
Yeah.
like a carousel, and you want it to move continuously all the time, right? But then if people jump on and off, it kind of reacts on that. So it kind of stops and it doesn't really work. You don't get the nice flow you want. So, but then if you add then a big rotating mass in there, or a synchronous condenser, then you continue to have this smooth turning all the time. So it's like you described as well. I think those are also good examples, like shock absorbers or something. There are many ways. It kind of creates a smoothness in the system, if you put it that way.
And you can understand it for frequency or for voltage.
Yeah.
It's a good example, I think.
And so it's not a motor, it's not a generator.
But it's the same machine, to be honest. It's a rotor and it's a stator. But it's not really a motor because you're not driving anything with it. And it's not then a generator because it's not connected to a turbine. So it's an electrical machine that you connect to the grid to provide then those services, as we discussed, like inertia and reactive power or short circuit power. But it is exactly the same machines, to be honest, with the stator and the rotor. So, yeah. a synchronous machine connected to the grid.
Now, I've heard it described as well as a natural response. Is that because it responds to grid events since it's physically part of the grid at that moment? There's no sensors, no software, no control loop. It's the same piece of equipment that would normally be on the grid. So natural response, would that be the right way to call it?
I would say it's a very good way to describe it, because sometimes my feeling is a little bit that we are getting too much in fancy equipment, where we need to control and to supervise everything. And based on the fact that we have so many units connected, solar, wind, HVDC links, STATCOMs, and all will try to give their contribution, we finally end up that they will interacting with each other, which is today a big problem for the utilities. When we speak about synchronous condensers, that is what is really nice with that. The response is based on physics. If there is a frequency change, the response will be based on this change in physics, change on the rotation of the machine. The inertia will be provided. No control functionality, purely physics. When it comes to fault current contribution, the current will be provided based on the impedances. How far is the fault away from your system? And we will provide that. You don't need to think about that. If you are using this power electronics, which I did, you have to think about how much current can I deliver? How much current can I deliver just now when I do also handling some reactive power? And maybe then there will be a contradiction, or you need to limit your response. And that is definitely something which the transmission system operator not want to have. They want a clear response when there is a clear situation. And that what you normally get from a synchronous condenser.
Well, I'd like to talk about more this natural response versus the maybe synthetic response that could exist. But I guess maybe a more basic question. I mean, ABB has been making these for decades. What has changed in your business over the past couple of years that has had you maybe refocus more on synchronous condensers?
We have delivered, like you said, a synchronous condenser for many years. And if we go back, way back, then it was mostly for reactive power. That was what it was for, pretty much. But then, like Kristina mentioned before, we have more power electronics, which has been working excellent. But now with this transformation of the energy system, with adding more renewables, more converter-based energy sources to the grid, and then also removing those big fossil fuel, it is like a little bit revival for the synchronous condenser, but then mostly for the inertia and the short circuit capacity. And I think when a few years back, maybe let's say 8 years back or something, we really saw this trend that had been ongoing for a while, but still things were starting to happening. And we got more requests for it. We saw opportunities around. And then we thought, let's see, what can we do here? So we kind of start to dig a little bit deeper into the business, the market, and also what is the customer really needing. Yeah, so then we thought we needed to to really take the opportunity to see how we can contribute with the synchronous machines. Because during all the time, we also then built synchronous machines, but then as motors and generators. But like I mentioned before, it's the same machine. So why not use it more like a synchronous condensers as well?
So for us, it was also a way of going away a little bit from a product supply to a more systems approach, where we said that, well, we want to add more inertia. So we developed a flywheel solution. When we thought that we need to handle a support to power oscillation, well, we developed power oscillation damping as a solution for that, for a synchronous condenser. So there's always kind of development going on also for the synchronous condenser. And you could ask the question, well, is there something very specific or strange with that? No, it's nothing strange with that. But you understand what is the consequence of that. For example, for the flywheel, we still don't have an international standard. So ABB is really stressing on that to speak about these flywheels and speak about flywheel security. Even everybody would like to increase the inertia, but we have no standards. In reality, it's A very important question which needs to be considered, and ABB is working on that.
It's for sure a lot of mass and a lot of power that's contained in this flywheel that is moving around. So we need to really think security and safety as well when it comes to those.
Like in the battery systems, when the batteries were coming, we had to think about fire security. How to add batteries, for example, in a big parking house. Well, is that good? Maybe. If we do it, how can we secure that the ventilation systems is not handling the gases? So we need to think about security as well. And I think that is one of the big changes where we did not only a product apply, we are more thinking about systems approach.
Well, I know that you two have been involved in kind of forming some of these contributions to the market, this global standard for what it should be. And I'd like to chat about that as well. But I want to get back to the point that you were making, Kristina, about how there's so much change that's happening to the grid. And now over the past, I don't know, maybe 2 years or so, there's been a pretty new and frankly an extreme stress test for exactly this capability of an instantaneous response to changing grid frequency and voltage, that this issue has arrived in the last few years, which is data centers, AI data centers. And they're behaving in ways that the grid has never had to deal with before. And I know that ABB has also recently participated or extended, rather, your partnership with Voltigrid. But they're a microgrid. And before we get to talking about a microgrid that's fully isolated and not connected to the grid at all, I wanted to first maybe talk about what happens when AI data centers are connected to the transmission network. And maybe from some of your technical discussions with data center developers, how do the load profiles of these facilities actually differ? Is it also invoking a synchronous condenser response for data centers connected to the grid?
So far, to be completely honest, what we have delivered and what we have worked closely with is really to see in the microgrid what the impact it has had there. So, because that's a challenge enough. But then to put it on the grid where it's a bigger system, even more complex. It becomes more complex. I don't know if we've done any study right there, to be honest, here locally. I was reading an article just last week, actually, about that right now we have not, from a global perspective, really put all those demands maybe on the data centers that we should have. And the article was more or less about, okay, there will be more regulations for the data center coming up because it's needed. Because it is, like you said, it's a load that has never been seen before. The load swings are so fast and so big. So we do need to manage that in a way. And it's for sure is a challenge.
Christian, I know you have experience. You're a technical guy. Can you walk us, what does this physics look like? Well, like when a data center is flipping from what Kristina was just talking about, drawing to now delivering in a tenth of a second. Why is it so destabilizing? What does it feel like to the grid?
Well, we always, when we are controlling something which should be stable, we want to control it and to counteract something. Now, if something is acting so quickly that you cannot react on it in the same way, in the same time frame, then it becomes a stability problem. So if your data center is drawing 100 megawatts, and then in the next half a second, it's not drawing a load at all because it disconnected, or the other way around, then this becomes a problem for the network. So that's the reason why we are discussing just now on a European level how securities or requirements should be put forward to data center operator and how they both can help in understanding the load cycles, what they are creating. Sometimes it's maybe even difficult for themselves to understand how quick the responses are coming because it's driven by AI. So it's driven by the questions and how many of GPUs are used in parallel to calculate the results of that. So for them, it's also difficult to make sure and to guarantee a type of load function which they can guarantee. They cannot really. And that's the problem for a transmission system operator. Now, the battery suppliers are then adding on to the data center, said, well, we can help in providing also some active power when something happens, and we can react quickly on that. And the power generation, like power engine, can say, well, we can also produce something more active power if the grid requires that. But the problem for the transmission system operator is, who shall control that when it's going so quickly? And that's the reason why I would like to come back to this physical response, because there the physical response is from the synchronous condenser given. You don't need to think about who shall provide you the response. It's just providing based on the frequency change or the voltage change, and you will get the response, how much the machine can do.
And to clarify, whether it's over frequency or under frequency, synchronous condensers can handle both of those directions.
Yes, it will respond based on both of over and under frequency or over and under voltage in the same way.
Now, Kristina, you mentioned this microgrid is kind of the focus for you guys at the moment. It's where you've seen traction, at least on the sales side, it sounds like. Can you talk us through the Voltigrid collaboration, how it came about, what problem they're solving for? Because I want to know what stability challenges exist in an isolated microgrid that requires a synchronous condenser, even when there's no grid connection at all. You said it's a big challenge. Tell us more.
The whole thing started actually I think it was in November 2024. Because this was not on our radar at all. So we were kind of surprised. So we got a request from a customer, or then Voltigrid here, who is a infrastructure power provider, and they've been working oil and gas, but also then data centers. So they contacted us and they asked, so we have some challenges with stability when we do our simulations for our data centers. And they had then a lot of engines, gas engines, that are going to then cooperate to have all the power needed for the data centers. And these are huge. We talk like hundreds of megawatts or gigawatts. It's huge. And when they put together their simulation and they saw we really need to do something here. So they started to look around, okay, could a synchronous condenser help? And then they contacted us. So we started working together and have done a lot of simulations just to see what is needed. And yeah, for their specific kind of loads, their specific equipment, the power generation. So you really need, it's a case by case study that is needed to be able to say exactly what this certain data center would need, or with this certain engine or this certain whatever it is load, what does it look like? But here we found a really good match, and we found that working together, adding this complete string for a certain amount of engines, we can really create that stability that is needed. So we have been, so a lot of work together to really find a good solution. And it's an extremely interesting business because things are happening so much faster compared to if we're working with like TSO projects or something. So it's very, very big differences, but very interesting.
I've got a question about how many synchronous condensers one needs. So you mentioned, a couple hundred megawatts, maybe like a gigawatt. I think with them, you've signed, I don't know, maybe something between 20 or 30 synchronous condensers.
We
how do you
have
figure
62 now.
Okay, so double, triple, double.
They placed an order now also in end March, beginning of April for another one. So they continue. They have a lot of building to do. And they have this power blocks, and it depends on, so I can't say the exact amounts, how big that power block is, but it's several units of, and that's also how big are the engines. So it differs. So I can't say anything general.
Well, I guess my question is, do you have like a ratio of power generation that like, maybe for every 100 megawatts, you have one synchronous condenser, but when you're expecting a lot of frequency change on the grid, that ratio goes down. It goes actually for every 50, you want one.
I wish it was that easy.
It's not that simple? Okay.
That would be really nice, but it's not. So what we're doing is really to look at simulations, as we're also looking at different type of power production units to see what is needed then. We're also looking, because we see maybe we will need that also when we have turbines, even though then we have actually quite a lot of inertia spinning there, but they might be actually supporting in that case also. So far we can't look at the past and see what is the right answer. We need to develop it while we're going, right? So
Custom carousel.
Yeah.
I guess just to clarify, is this equipment for the microgrid application the same equipment that you would use for on-grid applications?
More or less, it is exactly the same. It's the synchronous machine. We have the flywheel. We have the different kind of subsystems between to do that. We have this. So it is more or less the same. But then you optimize it for each single project where we have the reactances needed and all those parameters that is very customer specific. But otherwise it's the same. But here what we need to do is to really make sure that we can move fast, right? Because that is the whole data center, how they need it. So we need to make sure that we have it simple, put together. So it's a more modular kind of concept. But that it is in reality the same that we can use also for other applications or other type of customers.
Now this data center example, it's almost like an extreme case study in how fast and violently load can shift. And I think it raises a question that I imagine many listeners are already asking themselves, which is what you've mentioned a few times already, Christian, which is, could a software-based solution like a grid-forming battery or a StatCom respond quickly enough to handle this? So now I think we should, spend the time to unpack it properly. What is synthetic inertia? Because I think the gap between simulating inertia and physically having it is the real crux of the debate. So, Christian, I guess, grid-forming inverters and batteries, they can be programmed to behave as if they have inertia. What is actually happening on like a technical level when they're programmed to do that and when they do that?
You can say in general, if you would like to develop a power electronic solution which could simulate or copy a synchronous condenser, you can do that. The question is always how commercially interesting is that when it comes to the solution which you would like to provide. On a simple example, in the data center you will have a lot of active power jumps, ups and downs in seconds. What is the most impacting the lifetime of a battery is the charging and decharging cycles. For a synchronous condenser, the charging and decharging cycle, this is nothing like that. So the active power provided as inertia, it could be delivered how many times you would like to. Doesn't matter. It's not impacting the lifetime, really. For the battery, it is. And of course, that's a consequence. It's the same when you want to do a lot of other things in parallel. Maybe you would like to provide reactive power as well. As you don't only have active power variations, you will also have reactive power variations. So that means that you need to secure that also during that period of time, sometimes you would need more reactive power and less active power. And this, of course, needs to be calculated over the power electronics in detail, so that you don't create an overloading on the inverter. For the synchronous condenser, doesn't matter. You will get the reactive power, you will have your overload capability from a rotating machine, which is excellent, easily. If you would like to overload a power converter, it's not so simple. Very limited time. We speak even maybe microseconds time overloading capabilities sometimes when you speak about big amounts. So it's not so easy. So it's really coming down to the differentiation, what can those units do and how shall we secure that they are not doing half of it. So where I think where we should do more and could do better is in reality in combining the solutions, where you combine a synchronous condenser with his excellent fault current contribution and inertia response with a battery, grid-forming battery system, where you can use that for black start capabilities and maybe damping out overvoltage, which I create with my rotating machine. So there is maybe much more developing coming in future, which we will see, where we will provide combined solutions.
And we have seen some, not only from our own simulations, but also then from other institutes that have done some simulation with really good results looking at the combination of battery system and synchronous condenser. That not specifically data centers, but for all over type of applications. So a combination is one way, but there is also preferences in other ways. So I think it's a little bit of a puzzle to figure out which bits and pieces is needed in specific cases.
I also think it will be impacted very much by the models which will be available on the networks. If the models will be difficult to be provided by the battery suppliers or the grid forming converter suppliers, then it will create also a headache for the TSOs or for the DSOs to make good simulations, because the simulations are only so good as the model. And if you don't have the right model and the right input, your simulations will be a game, really, a hazardous game, because it could be wrong. And we have seen that in US, where solar inverters not reacted as they should. And we have seen that also in UK, where we had this blackout based on a big wind farm which was connected and which didn't supply what they should. And that's, I think, one of the other issues which becomes important. Reliable models, RMS and EMT models. And those models are for rotating machines. They're there and we can be provided. It's not an IP issue. But for power electronics, it's always connected with IP. And that's the headache.
So when you talk about these examples of where these inverter-based technologies didn't respond as they should have in order to support the grid as it wanted to be supported, this comes down to the fact that the models didn't exist or weren't anticipating this kind of event on the grid. Is that right?
Not necessarily, but it could be that some of the data, some of the simulations maybe were not done correctly, which needed to be adapted afterwards. For example, in this British event, it was the case where they afterwards need to update the HVDC link control system, which created this blackout in UK a number of years back in time.
I think it's clear to me now that the synchronous condenser is like a physics-based response, and anything that gets to be this kind of synthetic or programmed or needing to be trained on a model it's going to have, I mean, you mentioned this lifetime issue with charging and discharging for a battery, but even beyond that, I mean, it's what a sensor is detecting something, an algorithm decides what to do, the power electronic system executes, there's some latency that's involved, and maybe not everything is predictable. Do you see a future in which synthetic inertia will eventually be good enough? You know, maybe at 80 to 90% renewable penetration, will grids still need physical inertia?
I think maybe if we speak about really small microgrids, I could think that their synthetic inertia and normal only converter-based solutions could be good enough. When it comes to bigger grids, keep in mind that those bigger grids, it will always include rotating machines. We believe sometimes that in future there will be a grid without rotating machines. It's not. We need rotating machines in a lot of industries to provide the amount of force and the amount of energy which those can provide to drive a compressor or to drive a big pump.
It's a load, Christian.
So and big load.
Yeah.
So we will need those rotating machines. We cannot just connect them via power electronics. So because that would limit that capability. So we will always have a network with rotating machines. So and I think that is something which we should work with and use the disadvantage of those both technologies. I think there is another thing where sometimes I get puzzled about, and that is when we speak about reactive power. And reactive power, I said before, this is voltage regulation. And everybody is asking for doing quicker and quicker voltage regulation to provide a more quicker response. But in reality, I think that is wrong. We should more relax voltage control in a better way. We calm down a little bit. If we go back in 50s, there is no problem if you have a slight overvoltage in the system. You don't need to react very quickly on that. Today we have so many units, solar, wind, HVDC, STATCOMs, and all are acting on the same type of voltage, the system voltage, DC, and they would like to react quickly. And of course, this will create headaches for the transmission system operators. And if you then add additionally loads which are quicker than everything else can react, like a data center, then you have a headache. And then it's better to calm down a little bit and try to take it easy, and don't stress it too much, because otherwise how shall you handle that? I don't know.
And I think also looking at the overall system, and there is so much, both with data center and everything else, there is so much power needed, electricity needed. There is so much more different kind of electrification, things that are happening. And so the whole system is getting more and more complex and so much bigger. So we're going to need all different kind of technologies to make sure that we have a stability in the grid. It's not only synchronous condenser. It's not only batteries. It's a combination of everything. And that's both from a technology perspective, but also from a supply perspective, to be honest. It's not going to be able to have batteries for everything or synchronous condensers for everything or any other technologies. It's a combination that's needed.
Yeah.
Before we get to the more forward-looking outlooks, I want to talk about supply chain, but there's something I want to come back to that you were talking about earlier, Kristina, regarding geography. And I think you mentioned with this example with Voltigrid, when you're speaking to customers, that the conversation is always a little bit different depending on what the customer needs are. So when a customer comes to you with a grid stability problem, what does that conversation look like? Do they come to you knowing that they need a synchronous condenser, or do they present you with their project and you help guide the decision for whether they need a synchronous condenser or another solution that ABB has?
I think we see both, actually. Many customers comes, like I mentioned here, the data center in Voltigrid. They came, we have a problem. Can you help us solve it? And then we start working with simulations. And I would say many cases it actually start with some type of simulations. We actually provide the customers with our models so they can put them in their studies to see how does it help. So that's one way, and we work together to find, okay, maybe we should have a larger machine, or with or without flywheel, what is really helping here. But then, of course, there many times then they actually have decided, we think a synchronous condenser could be the right way forward. And then we get okay, then it is those different, it's the inertia, so the megawatt seconds, so what do we need? Or this is what we think we need. How can you do that? Or it is the reactive power could be there, or the short circuit power, what is needed. So I think those are the three main kind of measures they're looking for. So that would be the base, I would say, when we start working together. And then we can tweak it up and down a little bit, depending on what they see. But simulations, and then we look at those different performances, what they really need.
And what are the criteria that really drive their decisions? Is it do you see the demand concentrating where there are weak grids, or where there's a lot of fault current needs, or the different application? Is there any, trend?
One most common would be when they really want to integrate more renewables. That is where we see it. And that could be on islands, it could be in countries, but that is really, I think that is the main driver. Except then for data center, if that we've put that as a separate one. But otherwise, it is really to be able to integrate more and more renewables. So we see we've been working with Faroe Islands, for example. They have a target. They want to be 100% renewable by 2030, and to be that and still keep the stability of the net, we work together with them to see, okay, synchronous condenser is a really good solution. So we have now we have delivered 4 and the 5th is on his way. So they really, and it's working. And they already now are having a few days, I don't know how many days actually, where they have 100% renewables and it's working good. So that is one, I think, really interesting example. And we have a lot of islands actually that we're working with smaller grids, with more renewables and less big mass in the net actually. I don't know, Kristina, if you have some other that you think of.
I think you asked the question also before, what could be the question from the customer? It could be that the customer has a problem with stability, like in a mine, when you're far off in a grid, and they would like to stabilize that, and how can that be done? And then we are trying to provide them a solution to make their grid more stable in voltage or in inertia or whatever that may be.
Now I'm trying to picture, Kristina, maybe you can help me with this. How many synchronous condensers would an island need? Like, how many would the Faroe Islands need in a rough range? Because I'm picturing them kind of dotted around on the...
No, Faroe Island, it's not very, I don't know how much power they have there, but they will have a little smaller version, and they have one on some of the islands. We're doing one now, so I think it's also depending on how many, of course, how much electricity they're using, what type of industries they have, what type of loads do they have. So it's a combination. But they have one actually on some of the islands. But then we're working also on a project where they are now investigating how it will look like in Korea. So they're going to place one in together with it's their first one with a flywheel on one island as well, Jeju Island, to see how it's working. And then if it has the effect they think and the simulation shows, then they're going to place more. And I can't say exactly how many, because it is, like I said, it's hard to say. If you have this power, then you need this type of synchronous condenser. There is so much to it. So it's a little bit hard to say that. But it's I know a lot of different interesting projects.
I would say that one rough rule could be, if you take away a big thermal power plant, this thermal power plant, if you take that away and replace it with wind and solar, you will lose a lot of inertia, you will lose a lot of short-circuit current contribution. And the system is still very physical in the same way as before as it is now. So that means in reality something needs to be replaced in that respect. And that means that somebody would need them to deliver a synchronous condenser, or a combination with maybe a battery, also some synchronous or synthetic inertia. We still need, as I said, this fault current contribution, and this is something which is very special for rotating machines. And we need that.
Now, Christian, you'd previously mentioned in our planning call that Norway was a good case for where synchronous condensers were deployed. And I found that to be kind of a counterintuitive case, where even in markets with a lot of hydropower, there are scenarios where synchronous condensers still have a role. Can you walk me through that logic? What am I not thinking about?
Maybe we had some misunderstanding. I think if you take a market like Norway, where we have a lot of hydropower plants connected, hydropower plants in general are synchronous machines. Very often they are directly connected to the grid and would provide the system strength and support which is needed. But also those more and more hydropower plants are inverter interface. That means that they are running as a pump storage equipment, where they are linking up via a converter. And then there is no support of inertia. There is no support of fault current, because then it must pass the converter. So that means in reality, when you do that, you will reduce again the inertia and the fault current contribution in the grid. And then if you have then at the same time still some periods of time when there is very much wind, and as you know, also in Norway, there's a lot of wind connected to the network. Mm-hmm. It could be that during periods of time that there is so much wind connected, which means that the inertia is going down and the fault current in some regions are coming down. And fault current is something which is very local. You cannot transfer fault current from Oslo up to the northern part of Norway. So that means then you need to think about how shall we give this system strength up there if we don't have rotating machines supporting that. So that means in reality, system strength is necessary everywhere. And it has maybe different phases. Maybe in some countries where you have a lot of solar during daytime, also the solar behind the meter maybe will create more headaches for the transmission system operators and the DSOs than in Norway. So it maybe looks differently, but it's the same story. It's the requirements for system strength and who shall provide it.
And so I think from these examples, you've got anywhere from data center developers, renewable developers, new geographies, new applications that maybe wouldn't have been imagined in your sales pipeline 5 years ago. Would you say then that, demand is accelerating, and is the growth, coming from where you expected or somewhere that surprised you?
Going further, you mean, in the future now?
Yeah. Is the demand continuing?
Yeah, I wish I had the crystal ball. No, but like I mentioned before, like the data center, that was something that we did not think about. And there might be more of those, right? But we know there will be more data centers. So that will happen. But then it is what speed, and will it, because it's really US focused, the majority of all the projects, the majority of all existing hyperscaler data centers is in US. So I do believe that will continue. We also see with more renewables coming into the grids, and then a lot of islands, like I mentioned before, but also big system, like transmission system projects is happening as well. So there is all different kind, and I see also, like you were mentioning before, Christian, those kind of more industry projects where we see a mine that actually has issue, and also maybe they want to integrate renewables to their microgrids, where then you also can have a synchronous condenser to support. So it's, I think when we go back some years in time, we might have been a little bit more narrow where we saw that this synchronous condenser can support a grid. I think it's getting wider, the type of different kind of customers we can work with, what different type of issues that a customer have that we can support them with.
I would say also that the market for synchronous condensers is growing, and it will grow the next 10 years. This is my, not commitment, but I think my view, which I see in future.
And you mentioned this before, Kristina, that it's not just one technology that's going to win out, and it's going to be a mix. It's whether that be from synchronous condensers or different types of energy supplies. But it kind of had me thinking about the supply side of things. Is there a bottleneck to scaling up if the market's going to keep growing over the next 10 years? Is there a bottleneck to scaling synchronous condensers?
Well, I would say it's still a limited amount of players that provide large machines. So it's not endless capacity, even though there is capacity. So I don't see any issues now. But it also, depending on how fast it grows, how fast is the data center industry growing? How much of a technology will the synchronous condenser be in that field? And then also it goes the same with batteries. We do need to look at the combination. I think there are some sizes of machine. There are some challenges with the bottlenecks and so on, but otherwise it's with the growth pace that is happening now in which I think is a good thing. We need to increase more renewable to the grid. We need to do a lot of electrification. So it's a good thing, but it will still, somewhere is a limit, right? In what speed we can have in it. But so a combination, and then it's also depending on how fast we are moving.
And is there any limitation, for example, batteries, rare earth materials being required, synchronous condensers, I think you mentioned earlier, mostly copper, steel. Is there anything, from a supply chain constraint on raw materials that synchronous condensers would
No,
encounter?
that's a really good thing. With a synchronous condenser, it's copper and steel. That's it, kind of. So it's not any rare materials or anything like that. So from that perspective, it's a good. And what's really nice also with the synchronous machines is that you can actually recycle everything. I think it's like 98%, 97 something that actually is recyclable. So you could use it, but then on the other hand, you use it for 25, 30, 40 years. So it's not that you will need to recycle it so fast, but still, so the material can be reused compared to some of the rare material. But it's a little bit more difficult processes also to handle it that way. So from that perspective, a synchronous condenser is also
environmental friendly.
Yeah.
And one of the other topics that we were talking about earlier, Christian, as you'd mentioned, is regulation. And I know that you've been participating and working closely with the International Council of Large Electric Systems. You're not just selling equipment, you're also helping write these technical standards that will govern what grids are required to have. Now, going back to this point, does regulation now, as it stands, formally recognize inertia and fault current as required services for the grid? Or is policy kind of like catching up to this technical reality?
It is a wonderful question. I like that question. And the reason why I like it is that it depends very much on the country where you are. For example, in Sweden, our home country, their inertia is understood as free. But if Svenska Kraftnät, which is our TSO here, would like to buy some additional inertia, they would like to pay for battery systems and remunerate battery systems to participate. But that in the same time as a number of synchronous machines are running and providing the inertia, they don't bother that. So the inertia from the rotating machine is not income stream. If you go to UK, their inertia is an income stream. You get paid by availability of inertia. You get paid by availability of fault current contribution. And for that you get paid. And when the grid needs it, you will get already remunerated because you get paid by every half an hour a year you are connected to the grid. So there is a big differentiation between the different countries and regions, how they try to apply this to guarantee this system stability or system services. And there maybe this is a kind of political question, or it will be a question of standardization, but the last words are not said there. I think there will happen a lot of things when it comes in the European Union. We will have our NSOE and requirements for generators. We will have requirements for data centers. We will have requirements for big loads, how they shall behave, so that we don't get a problem with disconnecting big data loads or other type of loads. And this will continue because regulation is also a way of guaranteeing security of our grids. This is very important and it's needed, and we need to work on it. And in reality, everybody should participate. The load centers as well as the TSOs as well as the supplier. And that's the reason why this is so important. To keep that just open to the market, I don't believe really that. It needs to be a communication between the players, and then we have to find a way forward together. Sometimes for some of us, maybe this could be difficult or hard or costly, but also on the other side, nobody wins if we would lose the grid, and it would be a blackout. So we need to work there together, and I think that's a very important task, and we need to work with that.
And I really do see also that in the discussion, in the community and so on, we're not only talking about active power anymore. It's not only that, it's actually also about the stability and that we will somehow get the power. And I think it's shifting a little bit to be, that's part of the discussion as well on different levels.
And so maybe one last question for you both as we wrap up here. From your vantage point individually, what is one thing that you want utilities or developers or policymakers or the average Joe to understand about synchronous condensers in 2026 that they currently don't, that we didn't cover today?
Oh, I think we covered a lot, Bridget. But one thing that I think is synchronous condenser is nothing new. It's really been there. It's a proven technology. It's a reliable technology that we know for as long as we've had electricity almost. So it's really something, and like we have been talking about, you and Christian, a lot. Like it's physics. It's there if you have it. So it's nothing strange. It's something we already have there. It's a reborn technology rather than something new. And it will be needed going forward. 2026 and 2027 and going further as well.
I would also say that we still need rotating machines. We need still something like a wheel. Wheels are important even in the future. Even when we are a digital world, we will need wheels to run in cars or in pumps or in whatever. We need rotating machines. And the other thing which I think it's important, we need to think about supply management based on local capabilities. Even so, we would like to see the world as a common global goal where we can work together. But sometimes I have the feeling that we are not there yet. And we have tendencies in the world which are counteracting that. And that means that also from the supply point of view, it's good that you have resources available in your countries or in your regions or in Europe, which can help and provide those sources, both from the data point of view as well as from other type of mechanical engineering or equipment point of view.
Thank you both for joining us on the Interchange Recharged today to talk about synchronous condensers. I think it has been an incredibly helpful discussion to talk about where this technology comes from, what we might have been taken for granted and where it's going in the future and its continued importance, especially as we see data centers hopping onto the grid as well, whether it be on-grid, microgrid, whatever. But thank you both for joining us today.
Thank you very much.
Thank you.
And thank you to our listeners. As always, you can follow along the Interchange Recharged wherever you get your podcasts. See you next time.